Welcome back. So in this lecture, we apply some of the concepts that we have developed in the previous ones. And we perform a simple exercise that tries to illustrate several aspects we've been touching from a more theoretical point of view in the previous lectures. Namely, what we discussed was the overdamp dynamics and the associated Fokker-Planck equation, which I write once again, for the probability distribution configuration space of a particle or a system of particles, as X is a multidimensional vector, diffusing under the influence of a force, which I here express as the negative of a potential gradient. That's the Fokker-Planck equation. We have obtained a path integral representation, but what we did of the solution, what we did last time was to represent this probability density in a spectral form, which means as a basically linear combination of product of left and right eigenvalues of the Fokker-Planck operator, weighted with the exponent of the eigenvalues times time times minus 1. So in other words, this is the spectral representation of the to be more precise, of the conditional probability of finding a particle X provided that it started at X naught. And one of the consequences of this spectral representation that we investigated was that in the long time limit, so t much larger than, say, 1 over lambda 1 minus lambda naught, this could be written as R as a Boltzmann distribution or Gibbs distribution, plus a correction term, which I write here like R1 of x, L1 of x naught, e to the negative L1t, plus other corrections. And this is the first correction that you have when you look at the systems as it's almost approaching thermal equilibrium. If t is large enough, all the other terms here are exponentially suppressed. So this is really the time scale, the frequency scale to be precise, which controls how long it takes for the system to achieve thermal equilibrium. So all the properties that in the standard statistical mechanics course you give for granted, in your introductory statistical mechanics course you were saying, let's consider a system at equilibrium. We know the system attains equilibrium after sufficient time. Here we are trying to go beyond that statement and trying to look at the dynamics of the thermalization process and explicitly accounts for the time scales it takes the system to equilibrate. So we are really looking at thermal relaxation phenomena. Now, one might wonder, is this of any relevance at all? Because after all, we can always wait sufficiently long until the system attains equilibrium. So is this dynamical question sort of marginal, or is it quite central for describing physical systems of any interest? Well, at least in many cases, this is an extremely relevant question. For instance, most of the applications of stochastic dynamics to biophysical systems concern systems that perform transition while they are still outside equilibrium. For example, protein folding being the prototypical case, you have a polypeptide chain produced by a ribosome that is basically a 3D printer that takes the RNA information and translate it into a specific sequence of amino acids, which I here schematically report as little balls. And each amino acid comes in one of 20 letters. There are 20 types of amino acid, just as much as there are 3 colors or 1 charge in QED. You can think about it, amino acid being in 20 different charges, so to say. and and once you produce this chain, it is produced in a configuration that is not the thermal equilibrium configuration. What happens is that during thermalization, the chain attains configurations that are close to those that are basically sampling the Boltzmann distribution. And in the Boltzmann distribution configuration, Amphisa in 1963 showed that proteins are actually staying, oscillating around one basically single configuration. And therefore, that configuration is particularly important for biological purposes because it's the configuration in which proteins attain their biological function. Clearly, a very relevant question to address is how long it takes for the system and what happens to the probability distribution while the protein is folding. Because if you knew how a protein folds, then you can hope to sort of understand the folding process and understand how to intervene in the folding process to prevent protein from folding or to enhance protein folding, or understand how protein interacts with other agents during folding. This is just an example, and it's the sample that is closest to my own scientific interest. There are many others in glass transition theory, in disorder systems in general. Because disorder systems typically have an energy surface, a potential energy U of x, which is characterized by the existence of many, many barriers. And due to the existence of many, many barriers, there are long relaxation times, and there are multiple timescales associated with local equilibration and global relaxation. And therefore, understanding all of this dynamical process is largely at the heart of understanding many phenomena. And the more complex the system becomes, the later it typically reaches thermal equilibrium. And therefore, many of the systems we're interested in are still very far from equilibrium. On the one hand, we have the example of life, which is intrinsically an out of equilibrium system, because our equilibrium system is just dust. And while everything that is alive is driven off equilibrium. But also glasses are perennially, constantly out of equilibrium because it takes an exponentially long time to reach the crystal structure, of the system. That's my song, by the way. Okay. So today, after this long premise, we do a simple exercise and we try to understand a little bit more in detail how this thermalization works in a simple system. And the simplest system you can think of is not free Brownian motion, because in free Brownian motion, the system has infinite configuration space and will never attain any equilibrium. The system we look at is in fact much simpler. The system we look at is the next to simplest and is the harmonic oscillator. So we want to understand thermalization in an harmonic oscillator. So our setup is of a system with a potential U of x given by the usual 1/2 mw squared x squared. And we have a system at temperature, a heat bath at temperature T, a particle of mass m with a viscosity gamma. So if I look at the Langevin equation for this system in the overdamped limit, it would be T over kt negative, and then the gradient, and the gradient of this would be mx squared of x plus a random force. So there's a linear equations of motion for harmonic oscillator, as usual. That's fine. We can, of course, derive the corresponding Fokker-Planck equation for the probability distribution. We're working in one dimension, so let's do calculation explicitly in one dimension. So the question we ask ourselves now to begin with is, how long does it take a particle in an harmonic oscillator to equilibrate? How long does an harmonic oscillator driven initially out of equilibrium, how long does it take to reach the Boltzmann distribution? Well, luckily this is a problem one can solve exactly. And the way to solve it is you can either try to find the eigenvalues of these operators and solve this partial differential equation, which is of course possible. But the way I want to do that is by exploiting what we already know from our previous education. So we have to minimize the amount of math we have to dial in into this problem. So the idea is to first translate this Fokker-Planck operator in its Hermitian form, which is basically a Schrödinger equation, and then discover that we have explicit solution for the Schrödinger equation, and then use those to reconstruct explicit solution for this problem. So what do? We do the usual transformation we discussed in the last lecture. We relate. This is the the non-unitary transformation that transforms the Fokker-Planck equation into the Schrödinger equation. The resulting Schrödinger equation for psi is an effective Hamiltonian times psi equals lambda n psi n. So that's the problem we want to solve, where the effective Hamiltonian is written, let me write it here. So the problem we want to solve is h psi n equal lambda n psi n. H effective is negative diffusion coefficient second derivative plus my beloved effective potential. Now the effective potential is constructed, if you go back on the notes, you'll find all the details, d over 4 kt squared, and then it's a u prime square minus 2 u double prime. Now, if I explicitly evaluate this for an harmonic oscillator, let me do it here. I have a d over 4 kt squared. Now, the gradient of this guy squared is going to be m squared omega fourth x squared. Because when I take the gradient, I get m omega squared x, and then if I square it, I get m squared omega to the fourth x squared. And the second derivative is, of course, negative 2 kt, and the double prime, there's a kt here, and the double prime here is simply m omega squared. So the effective potential associated with an harmonic oscillator is still an harmonic oscillator, but it is a slightly modified harmonic oscillator. It is not the same harmonic oscillator. Because it contains an harmonic term with now a different coefficient in front. But in addition, we have this offset term here. And this is quite interesting, and we want to dig this. We want to dig this this difference and understand what it means. Remember, when we are dealing with Schrödinger equation, the Hamiltonian has the physical interpretation of an energy, and the potential energy that enters the Schrödinger equation is defined up to an overall constant. So really, the ground state energy can be redefined to be any value you want any global shift of the ground state energy will only involve a shift in phase of the wave function, which is unmeasurable, since you can only measure probabilities. So that's how quantum mechanics is telling us that energy is defined up to a constant. But now this, although it looks like a quantum mechanical problem, we should not forget that this is not, in fact, a quantum mechanical problem, and that the effective potential here doesn't come from any concept of work, and there is no such a thing as a phase associated with the wave function psi. So all these ideas that you can define things up to a constant do not really propagate to this problem. And in fact, we shall see that this constant here plays an important role. Without this constant, we would get completely nonsense results. So there's a lot of physics in that shift we get in the effective potential. But let's dig it out. To see this, let's make one step further and let us rewrite this object here in the following way. I want to write the Schrödinger equation, the standard Schrödinger equation, upstairs for a harmonic oscillator. Well, that's only the Hamiltonian operator. That's good enough. That's all we need. This is the Hamiltonian operator for the standard Schrödinger equation. And now let me write down the Hamiltonian for the following problem. So let me write these things. So instead of having this factor, we have simply d squared dx squared. So let me assume momentarily h bar to be equal to 1 in this Schrödinger equation, measure things in natural units. And then instead of having here these proportions, we have a term which contains the following thing. Let me dig out the factor 1/2. And then I would have d half kt squared m squared omega fourth, and then my x squared minus 2 kt omega squared m. Now, by writing these two equations one next to the other, we could in principle make a mapping and say, look, from the first equation I say that basically my diffusion constant plays the role of the reciprocal of an effective mass, right? Because wherever I see the diffusion constant in the Schrödinger equation, I will see 1/2m. So, which means that everything goes as if. Here I would replace this with my effective mass. So this here I could write 1/4 e, and then m is the physical mass, and 2k, the 2 already have, I have kt squared. Then I have x squared and minus 2, blah, blah, blah. So by doing this mapping, I could use the result I know from the spectrum of the harmonic oscillator, which I know, remember the spectrum of the harmonic oscillator is going to be omega h bar times 1/2 plus n. N is the principal quantum number. And basically dig out the spectrum of the Fokker-Planck operator. Well, this is of course something you can do. It is quite tricky, because you have to make sure you map each of these parameters into the corresponding parameters of the effective quantum theory, and then you work out what is the equivalent of the frequency and all of that. And that can be done, but it's quite long. Fortunately, and error prone, so to say. Fortunately, there is a shortcut we can use that is quite convenient in this case. And what is this shortcut? Is the following. Now, let's remember what does the spectrum of an harmonic oscillator in quantum mechanics looks like. If you remember, or if you go back on your introductory quantum mechanics course, you'll discover that the spectrum has two salient features. The first one is that each energy gap between one state to the next is the same throughout the spectrum. So, and that's clearly evident also from this equation here, right? You have h bar omega gap between the nth and the nth plus 1 eigenvalues of the Schrödinger equation. And the second salient feature is that the ground state has not zero energy, as a zero state ground energy or 0-point fluctuation. And we remember we discovered that this zero energy is due to the fact that ground state wave function is actually a Gaussian and therefore has derivatives and therefore has kinetic energy, which in turn is a reflection of the uncertainty principle. So we know that in the harmonic oscillator, the quantum harmonic oscillator, the ground state wave function is in fact h bar omega half. And once we know this, we have the spectrum, because it's enough to take the ground state wave function, multiply it by 2, and then add it to E naught, and we get the first excited state. And then, for the second state, you take E1 and you take 2 E naught, and so on and so forth. So why am I bringing this up? I'm bringing this up because I can use this fact, and now, without having to do any effort, I can tell you what is the first eigenvalue of the corresponding Fokker-Planck operator in the corresponding diffusion problem. Why? Because remember, now we use a second physics input that we have had from the previous lecture. The ground state now of the Fokker-Planck equation has zero eigenvalue because the Boltzmann distribution is a stationary distribution. It doesn't change with time. So in diffusion, lambda naught is 0. Now, then it's clear I can read off what is lambda 1. Because remember, if I look at in this equation, this is not the same harmonic oscillator as the one provided in the spectrum. It has a shift. And this shift is required to kill the 0-point energy. Without this constant term here, the ground state energy of this term here, the harmonic oscillator, would not be 0, would be the equivalent of the diffusion equivalent of this term. On the other hand, I'm required from the general property, since I know the Boltzmann distribution is the ground state distribution with 0 eigenvalue, I know that the real 0 eigenvalue is 0. So this means that the following quantity, 2kt omega squared m times d over 4kt squared, is actually the equivalent of this 0-point energy that sits here. So if I multiply this term by 2, I get my typical lambda 1. Because I'm bringing down, I'm considering twice this term here to get this term here. So in other words, if I multiply E naught by 2, as I did here, I get a typical gap between one eigenvalue and the next. So my first eigenvalue is given by this. So if I now look and simplify a few things, provided I haven't done any particular mistake, I arrive to this interesting relationship, which I always found very mysterious. And I try to elaborate why this is mysterious. So what did we actually evaluate in this exercise so far? That the time it takes to equilibrate in an harmonic oscillator is actually the following. Yeah. So if you look at this, it may look like a sensible thing. Why? Well, let's look. If the particle is very heavy, well, the time it takes to equilibrate. There's no really mass in the harmonic oscillator. This mass here comes from something we put there from the very beginning. So rather than using a mass time frequency here, we could have as well put directly a geometric parameter k, which was simply the second derivative of the harmonic oscillator. So let's say k is defined as m omega square. When you do classical mechanics, you tend to write m omega square here because you use this fact in order to have simple solutions when you look at the classical solution, because you get sines and cosines, where the m's cancel out, you get the frequencies of the harmonic oscillator. But in this case, this is not a classical problem, so it is convenient to leave the geometric interpretation instead than the oscillatory interpretation. What k means is that the larger k, the steeper the harmonic oscillator. Now, clearly, the larger k, the steeper the harmonic oscillator is, the fastest the equilibration occurs, because the system has a much smaller configuration space to explore before you reach ergodicity. So basically, K measures the volume of configuration space that is thermally accessible, and therefore, if the harmonic oscillator is extremely narrow, then the system simply doesn't have anywhere to go, and therefore thermalizes quite fast, which is okay, physically meaningful. Let's now take one step further and remember the fluctuation dissipation relationship that tells me T over m gamma. And this is instead a real physical mass now. This is not a geometric term, because this was entering the Newton's equation. This was entering the Newton's equation that we used to derive the Langevin equation. Now, something which to me is quite mysterious happens. I never kind of made sense of it, but this is specific for the harmonic oscillator. Temperature cancels out, which means that in an harmonic oscillator, regardless of what is the heat bath temperature, the system takes the same time to equilibrate. So if I take a particle in an harmonic oscillator and I double the temperature, even though I give twice as much thermal energy to the particle to go around, the system doesn't speed up its equilibration phase. And the reason I believe, but this is just my speculation, but I'm quite confident in that, is that the harmonic oscillator has this very specific feature to be a quadratic form Hamiltonian, both in kinetic and potential energy, which implies that you have an equipartition theorem both for kinetic energy and potential energy. So if you double the temperature, on the one hand, you have more kinetic energy, you move faster, and therefore you explore faster the configuration space. However, the amount of configuration space that becomes thermally accessible, the typical value of the potential energy, changes by the same amount because of the equipartition theorem. So basically you go faster, but you have twice as much to explore, and in the end, this maintains, these two effects cancel out with each other. That's my explanation for why the temperature here is gone. Finally, what we are left with are viscosity and mass. And that's quite normal, right? So if the particle is very heavy, it will take a long time to travel configuration space in a viscous environment. Of course, this is a viscous environment. So if you throw two stones of different mass from the Pisa Tower and you neglect air, they fall down on the same time. But if you throw them in water, where viscosity is actually a big factor, then you'll discover that they fall at different times, right? So mass in diffusive, dissipative environments does play a role in determining the time at which you thermalize. And of course, the more viscous is the system, the longer it takes the system to thermalize. So you could in principle go ahead and use your knowledge of the eigenfunctions of the Schrödinger equations associated with an harmonic oscillator to build all the left and right eigenvalues of the Fokker-Planck equation. You might remember from your previous education that the eigenfunctions of the harmonic oscillator are the so-called Hermite polynomials. And so in principle, I leave it to you as an exercise, knowing the spectrum of the harmonic oscillators in terms of Hermite polynomials, I don't remember the factors here. Let me just write the nth value of the harmonic oscillator eigenstate. Then you can construct the left eigenstates and the right eigenstates of the Fokker-Planck equation by taking this and multiply by the appropriate factor. And maybe I will take the chance one of these days to show you some application of these simple ideas to diffusive problems when I have numerical solution of Schrödinger equation, and I use this to understand, for instance, how does the probability distribution changes and all that. As I start from some initial distribution and let it propagate. For instance, we could have a problem using this information, a typical problem you would like to solve is like you start your configurations. You have an harmonic oscillator, and then you start many particles, say, with a position sample from a Gaussian much far away from the minimum, and you let these systems evolve, and they will propagate and eventually build up a Gaussian distribution in here, which is the Boltzmann solution for this problem. And this process, one could numerically verify, it takes place over a time scale of order lambda 1. I think it's an instructive problem to look at. We'll see later on if I can do this online. I have to rehearse this first to make sure that it is not exceedingly complicated. Okay, I hope you could follow this exercise. Try to do it on your own. If you have questions, just come back to me.